All right. So today we're using an old free response question all the way back in 1986. We had this really good example of a rolling without slipping problem. So we're given all the parameters. We're given the height. The sphere starts above the ground. It's a solid sphere. So it has 2/5 mr squared as its moment of inertia. And we're given the inclination angle. And we want to solve for quite a few things about this sphere in terms of the given quantities, as it's rolling and as it reaches the bottom in this case. So first, we want the translational kinetic energy at the bottom of the plane. So, well, translational kinetic energy, so kinetic energy of translation is just going to be equal to 1/2 times the mass times the velocity of the center of mass squared. Well, we don't know v, and we don't have that as a legal symbol we can use. So our goal of this problem is figuring out what the v is going to be of the center of mass so we can actually evaluate this function. So to do this, in any of these rolling without slipping problems, we typically use conservation of energy. So notice that at the top of the plane, it's at rest at a height above the ground, and then it's moving. So this is just going to be the gravitational potential energy at the top is going to be converted into two kinetic energy types: kinetic energy of translation plus kinetic energy of rotation. And we have formulas for all of these things. So kinetic energy of, gravitational potential energy is, of course, mgh. Kinetic energy of translation is 1/2 m times v of the center of mass squared. And kinetic energy of rotation is 1/2 times I times omega squared. And now we're just going to start evaluating some of these things. So first, we know what the moment of inertia is. And I'm just going to call VCM V, just so I don't have to keep rewriting it. I is 2/5 mr squared for the sphere. And now we have two unknowns. We have V and we have omega, so we have to eliminate one. And to do that, we're going to apply the no slip condition. So since it's not slipping, we know that omega is going to be equal to V over R, or V equals R omega. Doesn't matter which one we use. Again, we're given the fact that it's not slipping, so we're allowed to do this substitution. So we get mgh equals 1/2 mv squared plus 1/5 mr squared times v over r quantity squared, which gives v squared over r squared. Because again, the 1/2 and the 2/5, the 2's divided out. So, boom, boom, the r squareds divide out, which means that starting another column over here, we're going to get mgh is equal to 1/2 mv squared plus 1/5 mv squared. So adding 1/2 and 1/5, we get 5/10 and 2/10, which makes 7/10. And notice how the mass is going to divide out now. So we're going to get that v squared is equal to 10/7 times gh. So it's definitely not 2gh, which it would be if there's no friction and no rotation. So you could then just solve for v by square rooting both sides and get square root 10/7 gh. But we actually just need the square of v anyway. So we can just write that the kinetic energy of translation is just 1/2 times m times v squared, where this is the center of mass velocity. And we said that v squared is just going to be 10/7 gh. So we end up getting, after the 10 and the 2 divide to make 5, we get 5/7 GH. Or sorry, MGH. Oops. 5/7 MGH. And notice that is a unit of energy. So, for rotation kinetic energy, you actually could figure out the answer just by looking at the previous part and seeing that, well, we started with MGH worth of energy, and we took 5/7 MGH energy to put in our translation, which means that the missing 2/7 had to go to rotation. But just for our own consistency, let's prove it. So rotational KE is just 1/2 I omega squared. I for the sphere is 2/5 mr squared. And omega is just v squared over r squared. Notice the r's divide out again. And we just get 1/5 v squared, or sorry, 1/5 mv squared. When the 2's divide out again, so we get 1/5 times m times v squared, which is 10, divided by 7 times gh, and oh wow, what a surprise. The 10 and a 5 make a 2 on top, so we get 2/7 mgh. So you could have just subtracted it from the original, because energy's conserved. So notice that kinetic plus rotational equals the kinetic of translation plus the kinetic of rotation does in fact equal our starting energy. Now for some dynamics. Determine the following for the sphere when it is on the plane: acceleration and frictional force. Well, this sounds like it's time for a free body diagram. So first, this is the actual free body diagram before we use some components. So we're just going to use a blue label here for our weight force mg that acts directly downwards. Then for our normal force, that is acting directly out of the plane. And we'll move this just a little bit to the point of contact. So that's our normal force. And then it's rolling without slipping. And in order to create the rolling, we have to have a frictional force. And it is static friction. And that's going to go up the plane, always, for rolling. Okay. This isn't necessarily the easiest thing to read, though. So we're going to want to break the mg force into components if we want to write a system of Newton's second law equations. So we want net torque and we want net force. So to do this, once we're just gonna split our free body again. So I'm just gonna kind of redraw this here. So for our object on the plane right here, we're gonna have a friction force up. But then we're going to split the mg force up into two. Part of mg is going to pull us down the ramp, and part of mg is going to pull us into the ramp. So just from our dynamics experience, we know that mg sine theta is the part that pulls down the ramp, and mg cos theta is the part that pulls into the ramp, and therefore the normal force is going to exactly balance the mg cos theta into the ramp component. That's mg cos theta is the normal force. And then we have some frictional force up the ramp. So, writing a system of Newton's laws, equations. First, let's do F net. So first, if we do an F net equals ma, well, the net force is going to be the things helping acceleration, which is mg sine theta, minus the things opposing acceleration, which is friction, equals ma. That's equation 1. But then also, so that's going to be our force equation. Also, we can get a torque equation. So we can also write that net torque is equal to I alpha. And in this problem, the only thing that's causing a torque is friction. Because the mg force is acting at the center of mass, so we're choosing that to be our pivot point. And the normal force, since it's perpendicular to the surface, that's not generating a torque either. So our net torque is just going to be the things helping the torque, or angular acceleration, I should say, which is just friction times its lever arm, don't forget the distance for torque, is equal to I alpha. And that's it. So this is a net force equation, and this is a net torque equation. And we can simplify later on. So we're just going to put these together now. So mg sine theta minus friction equals ma. And then we have static friction force times its radius is equal to 2/5 mr squared times alpha. Another thing, do not bring in mu to this. Do not bring mu into this, because static friction does not have a set value. It has a maximum value, but we have no idea of knowing if we're at that or not. And the answer is we're probably not. So, actually, let's divide by r first. So, if we actually just divide by r first, so let's just cancel one of these, and then we add, we get mg sine theta minus static friction plus static friction equals ma plus 2/5 m times r times alpha. Notice the frictions do cancel. Then we get m, and I don't know why I changed from capital to not capitalized up here. So we'll make this a capital M, capital M. So we get mg sine theta equals ma plus 2/5 mr times a over r, because alpha is a over r when we're not slipping. Cancel, cancel. So we get mg sine theta is equal to 5/5 ma plus 2/5 ma makes 7/5 ma. The mass cancels, so we get a is equal to 5/7 g sine theta. And now the friction force is much easier to get from this. So for the friction force, we can pick either of these two equations to plug back into. And maybe just to avoid the moments of inertia, let's just use the force equation where we had mg sine theta minus friction equals ma. And we found what a is, so we just get mg sine theta minus the static friction force is equal to m times 5/7 g sine theta. So we get static friction force is just going to be equal to mg sine theta minus 5/7 mg sine theta, which is equal to 2/7 mg sine theta. And notice this, of course, has units of force. And one thing I neglected to mention for this previous part is there does exist a pretty easy kinematics solution to this, where since we already found v at the bottom, we could just use a variation of vf squared equals vo squared plus 2ad, where v squared at the bottom we said was 10/7 gh, so 10/7 gh equals 0 squared plus 2 times a times d, and the distance it rolls down the plane is just going to be h divided by sine theta, and you will get the same answer. Because after canceling the h's, you'll get 10/7 g equals 2a divided by sine theta. So after multiplying by sine theta and dividing by 2, you get, unsurprisingly, a equals 5/7 g sine theta. So if we found this clever, much easier approach, good job on you for connecting the fact that we already found v at the bottom. And you know we can't get away from some concept. Solid sphere replaced by a hollow sphere. Same mass, same radius. So we know that mgh is going to go into the kinetic energy of translation plus the kinetic energy of rotation. Well, mgh, and this is ke total in the parentheses right here, is the total kinetic energy. And well, this is the same. Same mass, same radius, so same mgh. So the ke total is just going to be equal to mgh, which is the same total as before. So this sphere starts with the same amount of energy. But now we're talking about the rotational kinetic energy. So mgh, which is the same, is going to turn into kinetic energy of translation at the bottom plus kinetic energy of rotation at the bottom. And note that what's different this time is we have a hollow sphere. So hollow means the moment of inertia increases compared to the solid object, because more mass is farther away. So before you had mass all inside the sphere, but now it's all on the rim, so I increases. So I increases, which means that ke of rotation increases. And that's our answer. So this means that as a consequence, if kinetic energy of rotation went up because moment of inertia did, well, that means the translational ke, and thus the speed at the bottom, goes down. So that's why the solid sphere is going to beat the hollow sphere in a race down the ramp, because the hollow sphere has a higher moment of inertia, so it's harder to spin up, meaning it's going to move less fast when you get to the bottom. But yeah, that's just a good rotation question. Does all your rolling without slipping things?